Good morning, ladies and gentlemen. Very quick video today looking at rationalizing the denominator. Now, we covered this quickly in class, but I thought it might be worth having a video anyway, and we have plenty of time to work on it. It's a very important skill, something you need to be able to do quickly. So, just a quick recap. Looking at this portion here of that example, 4a over root 7. The a is a constant. We can essentially ignore it in terms of rationalizing the denominator. What we want to look at is the root 7. Now, root 7 is irrational. Just remembering that there are two types of numbers, broadly speaking. There are rational and irrational. Rational numbers are numbers with decimals that end. So a half is equivalent to 0.5. The decimal ends, same with 3/4. The other type of rational number is the type where the decimal continues forever. So 0.333, etc. The strictest definition of a rational number is rationals are members of the family that can be written like a over b, where a and b are integers. So if you can write a number in the form a and b are integers, then it is rational. So all of these here are written in the form a over b, both are integers, then it's rational. And we might look at a proof in class to show that root 2 is irrational. Root 2 cannot be written in the form a over b. It instead goes on forever, 1.41, never repeats, has no pattern. Same famously with pi. So, how do we rationalize the denominator? Well, we, in this case, multiply top and bottom by root 7. So for the 4a, we're going to multiply that by root 7, and on the bottom, root 7 as well. Now, why are we doing this? Root 7 divided by root 7 is just 1, so when we're multiplying top and bottom by root 7, we're multiplying by 1 and not changing anything. Same with the root 13. Top and bottom by root 13, and let's see what happens. 4a times root 7 is very simply 4a root 7, nothing too exciting there. Root 7 times root 7 is 7, plus 2a root 13 over 13. Now, looking for a common denominator. What is common multiple between 13 and 7? Well, I don't know off the top of my head, and it's late at night, so 7 times 13 will get us one. It is 91. So we're going to multiply the top by 13. 13 times 4a root 7. And on the bottom will become 91 because we've multiplied top and bottom by 13. Once again, multiplying by 1. It's a trick we use a lot to make it look nice. So multiply top and bottom by 7 here, 14 a root 13 over 91. Then bring that all together, 13 times 4 is 52. So we have 52a root 7 plus 14a root 13 over 91. It's not pretty, but it's a single simplified fraction. Alright, what about something slightly more complex? Now, what makes this more complex is clearly there are negatives floating around, so be careful, and there are binomial terms on the bottom. So binomial meaning two portions or two pieces. We'll need to rationalize them slightly differently. Before starting, I'd remember that these signs we can just attribute to the top. However, when we attribute to the top, it's attributed to the whole top, so think about the top being in brackets. With the 2, it doesn't make a difference. With a 2 plus root 5, it does. You'll see why in a sec. So really, we can write this as minus 2 over 3 root 3 plus 7. Now, to rationalize it, we're going to multiply both top and bottom by 3 root 3 minus 7. Now, why? Because the difference of perfect squares. So a squared take b squared is equivalent to a plus b, a take b. And this very interesting property allows us to multiply by 1 in such a way that the bottom or the denominator rationalizes. So, just dealing with the left-hand portion first, that will be written as minus 2 lots of root 3, 3 root 3 takes 7, over, now, difference of perfect squares, I'll do this once over here, and then we'll do it more quickly from then on. That will be 9 times 3 is 27, minus 21 root 3, plus 21 root 3, minus 49. So 27 minus 49 is negative 22. Now, what you could do if you were going for a shortcut, you could do that squared, take that squared. Will get you negative 22. And that's what we'll do with the next one. Equals minus bracket 2 plus root 5 over, 2 root 5 plus 4 over. Now, first one squared is going to be 4 times 5 is 20. Take second one squared, 20 take 16 is 4. Alright, now, taking that. Yes, it looks like I've got no operation between them, but please remember that that negative there will count as our operator. Alright, so let's expand out the first set of brackets. Minus 6 root 3 plus 2 root 7, that's doing that, over negative 22. Now, I might just leave that as a plus, because you can think about that as a plus there, the plus minus, and multiply this negative in last. So negative bracket. Now, FOIL. 4 root 5 plus 8 plus 10 plus 4 root 5 over 4. Now, simplifying the top, we've got negative 8 root 5 minus 18 over 4. Not going to be pretty, but just a process now. So once again, we're going to use a multiply by 1 trick to get a common denominator. 4s and 22, 2 will go 44. So I'll multiply the top here by 2. So minus 12 root 3 plus 4 root 7 over negative 44. Plus, now multiplying top and bottom by 11. So minus 88, actually by negative 11. Plus 88 root 5 plus 198 over 44 negative. So multiplying top and bottom by negative 11, you can change every single sign. Now, common denominator, so we can write as a single fraction over negative 44. On the top, there are no like terms, so we're just going to rewrite the entire thing. Minus 12 root 3 plus 4 root 7 plus 88 root 5 plus 198. Now, strictly speaking, I suspect 4 can come out of all of them, so we should eliminate a common factor of 4. So minus 3 root 3 plus root 7 plus 22 root 5, 198 divided by 4. Yuck, doesn't go out. 4 doesn't work. 2 definitely works. Minus 6 root 3 plus 2 root 7 plus 44 root 5, 198 divided by 2 plus 99 over negative 22. And we will leave that there. Sorry that was such a long example. I really hope you watched that on fast forward. Can you please do that short quiz for homework? It is a selection of surd equations. Thank you very much.